Well, welcome back. I'm kind of hinting at a lot of ideas that we're eventually going to cover, and as I mentioned, this is kind of a sprawling chapter. There's a lot of territory, a lot of real estate to cover, so I understand if your head's swimming a little bit because there's a lot of ideas, but don't worry, we're going to spend a lot of time on each one. But with the skydiver, basically as velocity increases, the friction increases, the acceleration slows to zero, and forces are balanced. Once forces are balanced, that object is once again at terminal velocity, unchanging velocity. There's going to be no net force, and the force of gravity will equal the force of friction on that object. Now, not all forces are going to be nice, neat in x and y dimensions only. Sometimes forces are an angle, sometimes they're an angle compared to the object at large. But if that's the case, all we have to do is use a little bit of our trig that we so easily learned those many years ago. So if I have a force that's applied, let's call this FAP, my applied force, and I want to know, I really don't care about FAP, all I care about is my force that's applied in a certain direction. So let's call that the x direction here. And if that's the case, my Fx here, my force in the x direction, is going to equal my applied force times the cosine of theta, because this is my adjacent leg, this is the hypotenuse of this right angle here, and so this adjacent leg would be the cosine of that angle. And we're going to do a demonstration next week kind of showing you that idea. Now, we mentioned the fact that the normal force is Newton's third law in action. So if I've got a book on a desk, okay, all that's indicating to me is that, hey, my weight, the force of gravity, my weight is going to be equal and opposite my normal force. The desk is pushing back on the book with an equal amount of force that the book is pushing down on the desk. And my net force right here, the sum of my forces, is going to be zero in this case. But not all surfaces are going to be nice and horizontal. Sometimes forces are going to be at a slope, and we're going to be working with this quite a bit. So if this is the case, this is the free body diagram for this situation. You have a weight. That book has a weight. That weight is never going to be in any direction other than towards the center of the earth. That is going to be your weight. You have to know that that's down. The normal force is going to be perpendicular to your surface. So that has to be perpendicular. So that has to be a normal force. Now, here's where it gets a little tricky. This normal force is offsetting the force of this book on this slope. And so that would be represented by actually this component of this weight. Now you'll notice that that ends up being, let's add a couple more lines here to help us understand this. And this angle is theta right here. And so that means that that angle is theta by one of your angle laws that you learned many years ago. We can kind of, we could rehash what those laws are about why that happens, but these are going to be similar types of triangles. This leg right here is the same as that leg in this relationship. So really, this force pushing back is trying to respond to the force of the weight right here. And that is going to equal the weight times the cosine of theta. So my normal force in this case is going to equal my weight times the cosine of theta. Now, all other things being equal, if that's the case, if there's no friction on this slope, then here's what would happen. If there's no friction on this slope, then that means that there is actually a net force acting down this way, and this object will accelerate down this slope. Now, there could be friction on it. So if that's the case, we don't know that that exists. Now, if you're drawing a free body diagram, can you draw this net force down here? This, indicate that right there. And the answer is no. You don't draw net forces on a free body diagram. And I wouldn't even draw this component of this right here. I wouldn't even draw this component on this free body diagram. My free body diagram would just be this. Okay? And that's what we'll get to. It's only the forces acting upon it. Now, if I go to a website here, and here I've got an object, and I'm going to show the forces on this object. This object right here is moving at a constant velocity. Its weight and its normal force are going to be equal and opposite. Notice I didn't have any forces in the x and y direction. It'd be nice if this website did show that, but that's okay because we're going to be focused more with what we've got here. But I'm going to change this angle of inclination a little bit if they let me. I'm going to change that to 45. I'm going to reset this puppy. And now watch what happens to these forces of motion. Okay? So now it's coming up this slope. Now you see a whole heck of a lot of stuff going on here. They've got some forces here that they might not be wanting to represent here, but this is my weight. This is my normal force. This would be the vector component of the weight that's pushing against the slope. This right here is the vector component of my weight that's trying to pull me down the slope. These are perpendicular. The one pushing into the slope is going to be cosine of theta. The one trying to pull me down the slope is going to be the weight times the sine of theta, as we're going to see. Okay? And since this object is moving at a constant velocity, the force pulling up the slope, and we're going to presume that there's no friction here, I didn't add any friction, that this force pulling up the slope is going to be equal and opposite to the weight times the sine of theta. And again, I'm throwing a lot at you guys. I just want to give you a brief little introduction into this idea, so you have a little bit of something to go on. Now, if there is more than one force that is going to be acting on an object, we are going to actually find the resultant force of that. So we're going to add up these forces and act upon that. Let's put this in here, and we'll see what we get here. So if I've got two forces acting on an object, I want to find out the resultant. It's just no different than doing a little bit of Pythagoras here. Maybe I want three forces. I'm going to find out the resultant. I'm going to add up my vectors, no different than I did before. All my forces in the x and the y. We've done that. Working with force is no different than working with velocity that we did before, or displacement. So, that's a lot to tackle, guys. That's about 21 minutes of me yapping. That's more than my wife wants for sure. So, here's what you guys are going to tackle. I know you should probably prioritize the test on 2D motion for next time. But tackle this along the way. Gives you something to do. Keeps you one step ahead of the law. It's not very long. These are almost all entirely conceptual questions. We'll get into the meatier math part once you get through your 2D test. Okay? Other than that, hope you guys have a good day.